So I'm going to talk about a tool for fuzzing soft IPs today, and I'll also talk about some of the challenges with fuzzing hardware. So this is more of a general talk on challenges with hardware fuzzing, some things that I encountered when trying to experiment with hardware fuzzing, and also a framework that we are trying to build for fuzzing soft IPs. So a brief introduction. Probably I'm preaching to the choir here, but fuzzing, as you all know on the bridge, is an effective, proven technique to find security critical issues in software. And you don't really need to understand, in many cases, the internals of the software you're testing. That's the primary goal. And as you know, fuzzing is not to test the correct functionality, but we want to test and explore that unexplored or undefined area. So there are many tools that are available for software testing and fuzzing. But when you look at the hardware domain, there are new techniques and tools that are being explored today that are fast gaining traction both in the academia and also in the industry. So before I jump into the actual talk, I want to take a couple of minutes talk about common hardware verification methods that you may already be aware of. Hardware verification has different types of techniques that are employed. Simulation-based verification, for example, system Verilog test benches. These are very popular. System Verilog is pretty popular because it is software-like. It's got OOPS. It supports OOPS concepts. It's transferable skills with Verilog, and it's a semi-loosely typed language. So you can get away with certain things that you will not be able to with actual Verilog that gets synthesized into hardware. So you have some constructs that you could use for hardware verification. There are certain issues with this as well, like you won't be able to get coverage driven information from out of the box simulators out of the box, right? You have to tweak the test bench in some form to give you that coverage information. And in many instances, simulations can be slow. And if you try to parallelize them, you'll run into problems of bottlenecking, like you have your simulator generating a lot of test cases. I mean, the test generator generating test cases, but your simulator is slow. And you have to synchronize between different test case generators, drive good simulation efforts. So there are some challenges associated with this. FPGA-based verification is pretty popular and is really important, along with emulation. It's faster, closer to the hardware. You put your code on the FPGA or on an emulation system, and you can test the behavior. But obviously, there are setup efforts required. There are costs, but it is well worth exploring this as well. Formal verification is fast gaining traction. It gives you that exhaustive testing, that confidence. Formal property verification, equivalence verification are very popular. And more recently, security path verification is gaining importance as well. Like you have your output or your asset, and you can try to identify if there is a specific path from your input that reaches the output or your asset that you might miss using normal testing, like simulation based testing, for example. Obviously, formal verification techniques have higher effort, advanced skills, then you run into scalability and complexity issues when you're scaling from a small module to an entire SoC, for example. But there are a lot of advances now. There is some effort to make it more push button. So there is a much more concentrated effort across the industry to make it lower barrier to entry. So what we want to talk about today is this new approach that's gaining traction, and there are some research papers, not many, but there are some research papers talking about it. And I want to focus this talk on this aspect. You may already be familiar with converting C++ to, or System C code to Verilog code. One of the applications is I want to write a code in C, and then I want to put it on an FPGA or convert it into a synthesizable design. And there are many commercial and open source tools that support this. On the other hand, compiling Verilog into C++ executable or System C models is also fast gaining traction. And there is this open source tool called Verilator, which is supported by the Chip Alliance and the Linux Foundation, which is widely used in the industry and in the academia. This tool can be employed to convert Verilog into C++ executable code and binaries, for example. even System C as well. And the mere concept of working with C++ code and binaries opens up exciting opportunities to use AFL or some of the latest advances in fuzzing technology to fuzz these binaries and identify security issues. As I mentioned, there is some recent research in this domain. So I just wanted to highlight some of these. If you have time, you can look at these papers offline. They are pretty detailed. I found one in 2016 from a university in PRC, and a couple of other papers from a University of Berkeley and also Virginia Tech and Google. They are very similar in their approach. They talk about converting Verilog code to executable C++ and using software techniques for fuzzing hardware modules. I just wanted to take a minute to highlight what are the use cases that you could be looking at when you start fuzzing hardware. And these are just representative, it's not limited. Firmware testing obviously is obvious. Another interesting use cases you could look at is memory or IO transactions. Let's say you're trying to access a certain range of memory, and the transaction doesn't reply back to you, it just times out. You can find these kind of hang or timeout issues using fuzzing. You can also test for unsupported opcodes. Opcodes are really important in hardware. There are certain set of opcodes that a module can support and certain set that are not supported, and you want to test the behavior of the hardware with coverage when you input an opcode that is unsupported. Address protocol and conversions, you convert from a 32-bit to a 16-bit address, or you do protocol conversion from one protocol to another, convert data format, debug trace formats. Those are all really interesting areas where you could fuzz. And the other couple of things that are listed here are related to like secure transactions. You could access an asset using a specific ID, for example, and you could fuzz the access port. And you could also do some kind of privilege level access testing, cover entire privilege ranges. You could fuzz those privilege levels. The last one is really interesting. This is more of a data processing. If you look at a PCIe TLP packet, it is very strikingly similar or in format or in representation to like a TCP packet. So there are some opportunities here that where you could look at these TLP packets, malform some of these inputs, and try to understand how your hardware accelerator or packet parser is actually using this data and find some interesting behavior. Obviously, there are certain challenges that you would face when you start fuzzing hardware. I have a quick list here. I will go through each of these in the next few slides. But I want to call out the high level challenges that you would run into that I think native fuzzers that are out there may not be able to support today. So you don't have clocks and resets in fuzzers. You don't have hardware related hangs or crashes. That's an interesting area that I want to talk about. State machines are also very interesting. Verilog assertions, system Verilog assertions, how you can leverage them to find crashes and driving multiple stimuli. Your hardware module can consume a lot of different types of stimuli, including clock, reset inputs, enable signals. How do you fuzz all these different inputs? And finally, all Verilog is not synthesizable, meaning it doesn't end up as a hardware, right? You have certain constructs in Verilog that's very, verification oriented, like system Verilog constructs. So you have to be a little careful when you're synthesizing your Verilog. So your design under test could, you need to take some care on what's your design under test if you're fuzzing your actual hardware module or you're fuzzing some kind of test framework. So let's talk about clocks and resets. As you can see in this picture here, you have your clock signal that's varying periodically, and a fuzzer generally out of the box it doesn't generate this kind of periodic signal, right? You want your clock to toggle between different fuzz iterations, and this is very predictable. So natively fuzzers don't support it, you need to tweak it in some form, or if it supports it, then maybe I'm not aware of it. I need to learn more about it. But essentially, I found that most fuzzers don't support this clock concept. And they also don't support this reset. You can't reset your hardware module after like 10 clock cycles or 25 clock cycles. Or let's say you meet a certain condition or you transition to a certain state, and then you want to assert and deassert your reset in that state. So you don't have this ability with native fuzzers. Hangs and crashes are very interesting as well, like buffer overflows, application resource exhaustion, deadlocks, right? These are like software centric, but they can have a completely different context when you talk about hardware fuzzing. Hangs in hardware could be due to many reasons, right? You go to a different state, and then the hardware gets stuck in that state and it cannot transition out of it, or you go to an invalid state that doesn't have any further states out of it, or you're waiting for some kind of completion. For example, memory reads. You are trying to read certain data from a IO port or from a certain range of memory, but your transaction does not return, and these are supposed to be non-posted transactions, right? You actually are expecting return packets versus posted transaction. You just post data and you don't expect anything in return. You can simulate this kind of behavior using fuzzing, and this is something we will explore as part of the tool that I'm talking about. And obviously, crashes are very important. So anytime you write a system Verilog assertions that dollar fatal, dollar error, when I was experimenting, I was able to get the C++ binary out of Verilator, and all of these kind of assertions ended up with the crash. So it's easy for us to write an assertion and then identify that there is a crash and log that test case and replay that test case in a simulation environment just to make sure it works. That's a real bug. So the next challenge is state machines. This is very interesting. So finite state machines output depends on your current inputs, past inputs, current state, and your past state. So it's very sequential in nature and it's not combinational. And you have to drive your design under test to each of these different states in synchronization with your clock. And when you reset, you go back to some kind of default state. So you have to have the ability to manage this state transition in some form, and you don't get a native fuzzer, out of the box fuzzer, to understand these concepts of states and then use that to drive the next state transition. So that's an interesting area to explore from a hardware fuzzing perspective. Non-asserted failures, these are very interesting as well. So we talked about Verilog assertions, right, where you saw like the dollar fatal or dollar error. But when you talk about non-asserted failures, you really don't have an assertion there, but this could actually be an undetectable scenario or an undetectable bug where your assertions are missed. You didn't write an assertion, but your hardware still entered into an unexpected behavior, or some kind of potentially dangerous output was produced, or it's in an undefined state. For example, let's say you are trying to understand what are the ways to access an asset, and you only want to provide asset access to trusted agents. But in this case, if there is an untrusted agent that can access an asset and you don't have an assertion in your code, you won't be able to trigger a crash and you won't be able to find this bug. So that's a problem that I run into when when I'm trying to explore fuzzing for these hardware modules. And generally, I found that fuzzers need to be improved, or you need to have some kind of rule writing or constraint writing methodology where you check against certain constraints, and based on that, you can identify these types of failures. And this is where formal methods can excel, right? The depending on what kind of constraints you write, your formal method constraint, you can find these kind of issues that other types of tools may generally miss. And the other interesting thing that I found was driving multiple stimuli. So if you look on the right side of the screen, you'll see that there is a simple module, but it's got so many inputs. There is reset, clock, data, and there's so many other outputs as well. Driving this in accordance and synchronizing with the clock is going to be pretty challenging. And you want your fuzzer to be able to produce this format or grammar based test cases. There are many of them out there, and some of these combine capabilities with symbolic execution and provide you that coverage driven information and drive coverage driven test case generation. But many of them are like poorly maintained, or they don't get used that often. So this is an interesting area to have coverage driven fuzzing, which has format and grammar based test case generation. And I think this would be very important for hardware fuzzing, with at least with the methodology we are discussing today. And finally, the other challenge is, not all Verilog is synthesizable. Synthesizable Verilog gets translated into real hardware, right? It gets translated into gates, registers. But for example, if you write a simple for loop in Verilog, that means you're instantiating that many real hardware instances, and that's really not feasible physically. Delays, you would just write a wait statement, and these end up being implemented as clocks and flip flops. So you have to be cognizant about how you are writing Verilog, right? That gets synthesized in hardware. So you have to make sure that the design you're testing is actually synthesizable Verilog. And somebody who is more accustomed to C, C++, it doesn't seem intuitive to understand these concepts in the first go, but you get used to it over time. Nothing is rocket science here. So that brings us to the fuzzer framework that I wanted to talk about today. So let me talk a little bit about what soft IPs are. In the semiconductor industry, an IP is a reusable unit of logic that you give to your SoC or your customer, and they would integrate in their overall design, right? These are building blocks that go into an SoC, for example. And these are often provided as synthesizable RTL modules. You also have another entirely different hard IPs and analog IPs that go into building the SoC. But today we are just talking about soft IPs here, which are Verilog RTL modules. Verilog is pretty popular RTL modules that get integrated into a system on chip, for example. So this fuzzer framework that we are trying to explore is specifically for soft IPs. And the reason why we want to use a framework approach is when we want to switch between different fuzzers, like I talked about, format-based fuzzer, or something that just fuzzes a blob of data. You can have the ability to switch between different fuzzers and between different model generators, Verilog to C++ converters. That gives you the advantage of using more innovations. This is an area that we believe that there is a lot more that we can expect to grow. So this is a general workflow. Any test case, test bench setup works very similar to what we have here. You would want to isolate the logic you're testing, identify your IO signals, input outputs, and you write a C++ test harness. That's in what Verilator offers you is they ask you to write a C++ test harness, and then you can compile the test harness, including your Verilog code, where you call your Verilog code within your test harness, and there are certain constructs that you follow to make the seamless connection. And you would get your executable C++ binary along with the code, C++ code, and then you would be able to fuzz those. We are just using AFL++, but there are other fuzzers you could use here as well. And obviously you monitor for crashes and hangs, and like I said, timeouts would result in a hang, and anything that has a dollar error or a dollar fatal that you have an assertion results in a crash. But obviously anything that doesn't have these will be missed, and that's where we believe that writing constraints is very important in this domain. And finally, you would just review those test cases, replay them, reuse them in a simulation environment, just to ascertain that these are actual real issues that you're testing or you're finding. So there are a few issues that I mentioned earlier, and there are solutions for that to make this work more seamlessly. So the first issue that we encounter is state machines. So when you are trying to transition between different states based on your clock, input clock, your fuzzer needs to save the state at each fuzz iteration and then restore that state when it's taking you to the next clock, right? So Verilator gives you that ability to actually save a state to your disk and then you can restore it. So we are just leveraging that capability. Between each fuzz iteration, you save your state. Next fuzz iteration on the next clock cycle, you restore your state. The clock information is stored as well in the state, so you restore it, and then you drive your design under test to the next state. It's pretty straightforward. And you have this piece of code that's actually something that you include in your test harness. So it knows, the fuzzer knows that the executable itself knows that it's got to save the state before it goes to the next fuzz iteration. Clocks and reset are challenging, like I talked about. The challenges with clocks is twofold, right? You have to toggle your clock between each iteration, and then you have to monitor the context of the clock. So, is your clock raising? Do you want to go to the next state in your hardware when your clock is on a raising edge, or when it is on a negative edge, right? You have this context awareness of the clock that you need to be monitoring for, and both these issues are saved using the save restore ability of the Verilator. So when you save your model, you can timestamp it, and then when you restore it based on the timestamp and based on the clock context you saved in your previous run, you are able to restore it to the original state before, use that information, and drive the next state. Toggle the clock. First iteration, you toggle the clock and drive the design under test, and next time you restore it, you toggle it again, feed it to your design, and then you can take it to the next state. So you have this ability to transition between different states. You have the ability to let past inputs influence current inputs, past states influence current state and input and output. So that's a very interesting way to look at it from a fuzzing perspective. And finally, you have resets. Resets are very similar. We can, using the save restore ability, we can trigger a reset at random. We can trigger it. I meet this after n clock cycles. I want to trigger a reset. Your test harness can accommodate that, or you have a specific condition that you met, and you can trigger the reset. So these are like challenges that you could solve using Verilator and some kind of custom scripts. But having this kind of capability supported in a native fuzzer for hardware fuzzing would be really useful. And finally, driving multiple stimuli. You had an example where you had multiple stimuli to your Verilog model. Many fuzzers don't support grammar-based fuzzing, but there are fuzzers that do that. Peach was one of my favorite. I could say this is mutable, this is not mutable. I could control that capability. I'm assuming there are many fuzzers out there that provide that and combine that with symbolic execution, with coverage-driven execution, test case generation. So what we are trying to do right now is basically take your fuzz blob, split it bitwise, and feed these different bits to your input signal. So you're able to control your inputs, different inputs, and drive them at the same time. So this is probably not a perfect solution, but it works. But there is scope for improvement here with native support for this kind of efforts. So I have a toy example here. This is basic, Verilog. This is in fact not synthesizable. I just wanted to show that here you have an access to an address where the first if condition, you're trying to access a specific set of data, and then it gets stuck at that transition. It doesn't get out of that if condition, and you're stuck in a timeout mode, and then you have a dollar error here, incorrect address is being accessed, and you end up in a crash. So these are pretty simple, you can find using fuzzing. And obviously the method has its advantages and limitations. Advantages is free, open source. faster, lower barrier to entry. Everything's open source. I can set it up in half a day and start fuzzing Verilog. Easily parallelized. I can deploy this in multiple VMs in the cloud and get teams to work on it, write some scripting and make it more seamless, integrate in their environment. It leverages advances in software testing, better tools, better fuzzers. We have better testing capabilities. The limitations are that it's an emerging area. It's not very well documented. People are working on it. The existing fuzzers are software oriented. We need some enhancements for hardware fuzzing, and it's only as good as your cycle accurate model, right? That's the crux of this. So you want your models to be good representation of your hardware. So that brings us to the end of the talk, and the key messages that I think are important here is obviously bugs in RTL can end up as hardware defects, and we want to get to them early in the life cycle. So hardware fuzzing using Verilog to C++ conversion is a emerging technique. It can provide a powerful complementary capability to what we looked at earlier, the common methods that we discussed. And to make it all happen, a shout out or a call out to the fuzzing community is that fuzzers should evolve to natively support hardware fuzzing, understand the constructs like clocks, resets, multiple inputs, state transition, and also help with constraint writing that formal verification tools have. So that would make it even more useful for this kind of hardware fuzzing.